Hello, this is Xfixium again, and welcome back to how to make a Master System game using Devkit SMS tutorial number 9. In this tutorial, we code some commonly used functions that will be used throughout the game. This will cover resetting global variables in VRAM, updating map and VRAM data, and eventually lightly going over Metasprites. We will also learn about for loops and bitwise shift operators and when to use them. Let's dig in. Okay, here's some cleanup from our previous video. I'm going to bring in the rest of our audio files that we're going to use for the game. Here you can see them. I brought all the audio background music and then the sound effects I brought over here into our project. And if I didn't state this before, I will here. There is a GitHub link to this project that you can get these files from, so you can use them as we're going along in this tutorial, and it'll be in the description. And it should be in every tutorial description, even the previous ones. Okay, so I'm gonna uncomment this out, and I guess I could go over to comment or uncomment a block of code real quick. You can hit and hold control and then /, and that'll uncomment out a block if you have it commented, and then you can hit control / again to comment it out. So it's a shortcut. So I'd select this text and control / and then it will uncomment what I have already commented out, and I'm going to do the same here. And then what I'm going to do is build or use the asset build batch file. And again, another shortcut when you're in the terminal is you can just press the up arrow key and it will cycle through history that you did on the command line or within the terminal. So what I want to do is get to asset build.bat, and I'm going to hit enter, and hopefully everything builds. Okay. As you can see, our bank 4 went down a bit from what it was. It was about 10,000 K, I think, and now it's down to 7,000. But here, as you can see, all our constant stat assets to banks created are fully here. So we're ready to rock and roll, and we're done with our audio source file. Just to clean up some loose ends. So I'm going to save that. I'm going to go here in main, and I'm going to get rid of this. This is for our test. You know that everything works. So that's that. So we're going to start on our common source code file, and we're going to start setting up some functions within the common area where I have it under this source file because it will be commonly used throughout the entire game. So I'm going to start with a function that's called clear sprites. It doesn't return anything, and it doesn't expect any arguments or parameters. All it does is it calls two Devkit SMS functions. One where we initiate or we tell Devkit SMS that we're starting to define sprites. And then this next call is where once we define all the sprites, and there's a bunch of functions that Devkit SMS provides for us to do that. Once we add all those, then it will copy all that data to the or send all the data to the VDP, so it can put that sprite data within the VRAM, and then that essentially displays the sprites on the screen then at that point. If we don't put anything in between these two calls, it's essentially clearing out the SAT, and sometimes we need to do that. So we have sprites on the screen, but then we move on to another game state, which I'll show you what that means. And we want to get rid of those sprites that are on screen. This is how I call that, to wipe out the current on-screen sprites. And again, I'll do that when I need to reset the game state or something of that nature. So that's all this does. And I guess you should cover the unsafe. There's two versions of this. One is everything that's Devkit SMS related for the most part is it starts with this prefix of SMS. So there's actually another function that Devkit SMS provides that is just without the unsafe prefix here. So I will go into that later, what unsafe and safe means when we go to use these functions. Primarily what it means is when it comes to unsafe, we can't call the code while the display is being actively drawn. And if we do, you'll get some sort of glitch on the screen, most likely because of doing that. So there's times when you can do it unsafely, and that's usually right after the V blank. So again, I'll go into more detail when we get to it, but I figured I'd at least talk about it a little bit, why there's this unsafe version of this call. Clear VRAM, again, doesn't return anything, doesn't take any parameters, and all this does is we use the Devkit SMS function provided for us, and what we're going to do is we're going to clear out the VRAM up to where the tile map data starts. So this will clear out where essentially we would have tiled data at. So from the beginning of the first half of RAM, and then it'll go into the second half of the RAM, a total of 448 tiles. We're going to clear it with the value of 0. So here, there's 3 arguments for this. It's where we start writing the data in VRAM, the value that we want to write in VRAM, and then at the end of it, how much of the VRAM are we going to write to? And that's what we're providing here. So we're going to write up to the tile map data, and we're going to use 0. We're going to fill all that information with 0. So we're essentially clearing it out, and then at the end we're calling clear sprites that we have already defined here. And then we have our next one, clear screen, which doesn't return value, but we do have one argument that comes in there. So this will clear out the rest of the VRAM in the second half of VRAM, or the bottom section. The 2048 bytes that still remains. And there are times when I want to clear out one over the other, so that's why I have these two functions. It essentially does very much the same thing as our first one here, but this time we're saying, okay, we're going to start where the tile map data is, so it would be essentially this number here, and then we're going to wipe out the rest of the 2048 bytes that are left in VRAM with a given tile ID this time. So something that it might not be 0, we might want to clear it out with something else for whatever reason. And this is just a global variable. So all those globals that we created in our previous tutorial, or a previous tutorial I should say, we want to sometimes reset those depending on the game state, so that's where we're doing this. We also do make some Devkit SMS function call. So here again we clear out the sprites. There's hardware scrolling that's available with the Sega Master System through the VDP, so it can scroll the screen horizontally and it can scroll the screen vertically. And if we're in between game states, sometimes we want to reset that. So here we're resetting those values back to 0. And then there's another concept when it comes to the Sega Master System. There's a thing called line interrupts, and you can set it up through Devkit SMS again, where you can say, all right, I want this interrupt to happen at X amount of lines, and lines we call, that's the scan lines that are available on screen, and we'll go over that when we get to it. But we were setting all those functions or those variables. So here we're resetting to 0, and then here we're disabling the line interrupt altogether, so no interrupts will happen. Again, I'll show you what that means when we get further along. Reset scores. So this is where we're going to reset player 1 and player 2 scores. If you recall that this scores is from the global variable. If we look back on that, we can take a look. Here it is. That's that line that we copied from the top of the tile map. So it would be the line here that we copied. And what we want to do is, when a game starts up, we want to clear the character representation of the score. So we need to go in here and change these values. So right now they're at 259 for 0, and that's what we're going to use. And honestly, we could have made it defined for this, if I'm being quite honest, because not that I see this changing, but it could. But what we're going to do is we're going to reset those positions with the empty or the 0 tile. So I don't think we've went into more depth about the for loop than what was on main. Main doesn't have any of these arguments. As you notice, it's empty. That's essentially saying run this forever until we get out of the game, like I said previously in another tutorial. Here we're actually going to give it its conditional. So the conditional that we start off, and this is typically how C programming instantiates its indexer. So I is the indexer, or what will be going through the array. Scores, as I said before, is an array. As you can see here, it has 32 elements in it, so we'd have to go through certain portions of the scores to change it to the tile ID that we're looking for, which is 259. So how we do that? So we need to start, we're going to start at the third element. So we're going to say I is equal to our third element. How do we get that? Why do we use that number? We use that number because if we call here, I'll go off of this and let's turn on invert. If we go all the way over here, now remember we have this whole line as a array. It starts at 3. So 0, 1, 2, 3. So that gives us this tile within that collection, that array, or however way you want to look at it. So that's where we're going to start. We're going to start at 3, and that's what he said, 3. And then we're going to go 6. So from 3, 4, 5, 6, 7, 8. So this last one in the array is 8. So from 3 to 8, this is what we're interested in clearing back into these zeros later in the game, because this will change, and then if there's a game over and you come back to the tile screen, it will show the first player and second player scores from the last play, but once they start a new game, well, we need to wipe that back down to 0 again. So that's what we're trying to do here. So again, we're going to start at 3. So 3 is where we're starting, and then we add 6 to that, and that gives us 9. And I'll tell you what this section is. These are separated by semicolons. So our first one is where we're going to start. Typically we usually start at 0, but in this case, since the array, that's where our player 1 starts, we're going to start at 3. So I equals 3. And then what this says is, this is every time this loops, it's going to check. This is our conditional. If this becomes true at any point in time, well, if it becomes false at any point in time, then we're going to break out of the for loop. So we're going to always check, okay, is I less than 9? So in the beginning, it is 3. So 3 is less than 9. It's like, okay, that's true. Then we're going to run our loop. So As long as I is less than 9, it will run this loop. And then this here is what we increment the indexer with. And we can increment it with various ways, or we can de-increment it in various ways. But here we're only interested in incrementing it by 1. So we say I plus plus, we're going to add it. If this conditional is still true, we're going to add 1 to I. So in the first iteration, it is 3. So scores, and then we're going to give it 3 because we started at 3. And what's going to happen if we go back to that global is going to go 0, 1, 2, 3, much like it shows in our tile map. This is the numeric representation of that. So it's going to go 0, 1, 2, 3. It's going to start at 3. And then once that happens, we're going to set that element in that array, the third one, we're going to set to our 0 tile ID. So that's where this 259 comes from, again, from our tile map. If 0 was at a different tile, then we would change it to that tile. Say it's like we put the 0 or all the numbers at the end, that will be a different tile ID at that point that would set on this array. So third one, we're going to set to 0, and then it's going to check again after it adds 1. So after this, it now becomes, after it gets done with this and we come to the end of the loop, we now add 1 to it. So now it becomes 4. So then when it's 4, it's going to check, is this still true? Is I, now that it's 4, is it less than 9? If that is true, which it is, then again, we're going to go into this code. We're going to go in this code block. And now I is 4 at this point. So now the fourth one in, I'm going to change to 0. So again, so we go, we start at 3, then on the next loop, we're now at 4. Oops, as I take out the number. Should put this in selection mode. There we go. So this would be 4, and then when the next loop comes, 5, then 6, then 7, then 8. And as you can see, we're going to change it to that value as we're iterating. And then at one point, so when we're at 8, it's going to add, and now it's going to be 9. So I will be 9 at some point. 9 is not less than 9. It is equal to it, but it is not less. So at that point, when this doesn't become true anymore, we kick out of the for loop, and then we process the next set or the next lines of code. And that's how a for loop works. Essentially, there's different things you can do with the for loop, but this is primarily what it's used for, to iterate through a collection of values, like an array or a vector or a list or whatever you want to call it. But here we're using arrays, so that's what this does. And it does the same exact thing for player 2, but as you can see, we use a different, we could probably use the same iterator, but here I give it a different iterator, which is J, and we're going to start at 23. Again, that's because that's where player 2's score starts. So if we go over to player 2 and we hover over this and we look down here, you can see that tile X is 23. So that's why we're going to start here. So, and then when we move over to the right, it's now 24, 25, 26, 27, 28. So again, we're going to add 6 because it's 6 places to 23. That will be 29. And then we're going to do the same exact thing. We're start at 23, then I'm going to go to 24 through this, and then 25, and it's going to keep going until it equals 29. And then this doesn't become true anymore, this conditional statement, and we're going to kick out, and then we're done with our work here. So that's what this function does. Next one, here we're actually returning a value. So a car, or a value from 0 to 255. Here we're only going to use it as a flag, and I do this typically. Again, you can use bools here, so it could be true or false. That may be more your style, however you want to do it. And but here I just use a car as 0 or 1 as the flag. Oh, of course you would. And then we handed a parameter or an argument, and so this threshold is, as it says through here, we're going to increment the timer. So this is our global timer from the globals source, and we're going to increment it by 1 every time this this increment timer is called will actually do what it says here and increment it. So, and I'll show you code where we use this. So sometimes I want to wait X amount of frames before I do something, and I'll use this increment timer and within the game loop, and I'll keep checking, okay, did we reach the threshold, whatever that threshold is. Say I'm waiting 60 frames before I do something. A lot of times what I'll use this for is I'll wait X amount of frames, and then once the threshold is met, then I'll increment the substate, so we go to another part of the game state through the substate. And I do that quite often, especially with the cutscenes, because they have their own events that happen throughout the cutscenes, and you want to keep track of what event you're currently on during that cutscene. So that's what this is. Well, I'll use this for primarily. What happens is it increments the timer, then it checks, okay, is that timer greater than or equal to the threshold that I'm given? If it is, we're going to reset the timer. We're going to return back to the calling code. Okay, we've reached that threshold with a 1. If it hasn't met that threshold yet, we're going to return 0. Hey, we haven't gotten there yet, but we're going to keep incrementing until we get to that threshold. Let's see, 2 more functions here. You have set RNG. This is for a random number, where we would set a base number to it, but then we will also add the frame counter. As you may have recalled, the frame counter gets incremented every vertical blank or every frame. So we're just setting that global variable at that point. And then get RNG. This is new because we haven't seen the shift operator. So these 2 arrows that point to the right, this is what they call a bit shift operation. The Z80, the hardware, the CPU itself doesn't support multiplication, and it doesn't support division. So the idea here is, instead of, if it's a power of 2 number that we're dividing by, we can use bit shifting instead of coming up with either our own solution for doing multiplication and division in software, which multiplication and division is basically essentially adding the same number over and over again X amount of times. We could roll our own version of that, or we could just, if you want to times something or divide, we use the multiplication symbol or we use the division symbol. And then in the background, when SDCC compiles, it most likely optimizes that call in some way. I do not want to hand SDCC multiplication or a division. It might be optimized for, but a more clear-cut approach and a more efficient approach is just the bit shift if what you're dividing by or multiplying by is a power of 2. So what are options for power of 2 and how this works? So if we go to power of 2 here, on the left side is the bit. So it's going from it's going up to 16 here in this table. So this is the bit, and when we shift it by X amount of bits, it will represent a maximum value, as we have been doing. So as I said, a byte is a number from 0 to 255, which are essentially 256 total values that you can have. So a byte is made of 8 bits. So here at the 8th bit, it's showing the maximum value that bit can represent. And we kind of went over that with some of the things that we talked about with the tile sets. When we go back to what Maxim is detailed, we said it was 2 bytes here, so that's actually 16 bits. And we said our first 8 bits here is part of the time number, but we need the 9th bit to get a value to go higher. So to 511. So here, when we go to 9th bit, it's telling us that's our maximum value at the 9th bit. That's why we use the 9th bit, because again, our 2 sections of VRAM can hold technically 512 tiles, even though those last 4 rows that we discussed before, the last 2048 bytes are used for something else other than tile data. But technically, we need a number that can get us to the highest amount that a tile can be, or tile ID can be. So that's why we use 9 bits. But here we're talking about a byte, and a byte again is 8 bits, the maximum value of 255 from 0. So that's 256 values altogether from 0. So why is this important, and how are we going to use this? So what we can do, as long as it's a power of 2, is bit shift to do the multiplication or division. So how would that look like? So here in our get random number, I'm going to hand it a power of 2. So that number that I'm handing is the bit. And what I mean by that is this number on the left. I'm going to hand it the bit that we're interested in shifting by. So that's what we're going to hand in our argument here. So I would hand it that bit, and then here it would, if we're shifting to the right, we were dividing. If we use 2 to the left, we are multiplying by a power of 2. So essentially, even though that's just bit shifting, that's essentially what we're doing here. So when we first get into, we're going to add an offset if there is one. There's not always an offset, but sometimes there are, like I described when we talked about global variables. The ghosts have that 64, the offset for the randomization that starts from 0, but it's 64 in increment. Sometimes I'll use that depending on the call. So it would add that offset to our RNG. Again, remember our RNG can only go up as an unsigned car, so it can only go up to 255. So we're going to set that, and then what we're going to do is we're going to divide that by whatever power of 2 that we have, that we send to it. And again, as an example of this, we go back to our bonuses. And remember, our bonuses have 32 elements in here total that could be picked from, and each one of these represents a bonus item. So 0 is cherry, strawberry, and so on and so forth, till we get the banana, which is 6. So when we start to randomize these bonus items later in the game, we want to take our random number, which remember can be a maximum of 255, and we want it to be divisible by 8 in this case. All right, so we want to divide it by 8. If we go back to our chart, we want to divide it by 8, then we will use the bit 3 for that. So essentially, whatever this number is, so as an example, if, say, the random number generated at the time, again, we can only go up to 255. Say it's, at the time, it's 243, or for whatever reason. What we want to do is trying to get a range of 32 values out of this number. So we can divide it by 8 to get a range of 30 from 0 to 31. And maybe I should show how that works from maximum value. Say we're all the way at the maximum value in our random number generator. It's 255. If we divide that by 8, that will give us the maximum value of 31. So essentially what we have here is, by dividing it by 8, we're getting a value from 0 to 31, which is 32 values, and that whatever that random number comes out of that division, we can use it to point to something in this array and then pick that through that random number, and then that's how we would get a random fruit out of this sequence of numbers. So let's say it's a different number. Let's say our random generator is, say, like I said before, 241 or something like that. If we divide that by 8, it will now go to element 30. So it's going to hand back or return 30. Then we're going to go in here, and we're going to go to the 30th element, which I think is this one here. And then that particular bonus is the strawberry. So then when that comes back, we pick that randomly out of this list or this array, or collection, and then we hand it back to the bonus entity, and then it knows that's the type it's going to set for its bonus. So again, we're going to send in one of the bits, again, whatever you want to divide it by. If we divide it by 255 by 16, so we have 255 and we divide by 16, that allows us to have 16 options in the range. So it'll be 0 to 15, 16 options altogether. And then if we would go lower, so if we would take 255 and we divided that by 4, now we have 64 different options that could come back in the range. So it would be a range from 0 to 63, 64 different values that could come back from this random number generator. And that's how it works through this function. And I use it in a bunch of places where we need to have random numbers. So again, like for instance, when the ghosts need to find a way to randomize them, when they're frightened, once they get in an intersection, they have to figure out, which way to go randomly, and that we can also reduce it down to 4 different values that it could possibly be, and then we can iterate through those 4 values, check if there's any collision detection or walls that prevent us from going those directions, and then we'll pick a random direction to the available ones that the ghost has access to when it's in that intersection. And it might only have one way it can go, and if it only has one way to go, then we're just going to go that way. Again, we're going to avoid doing a colossal amount of calculation based off of that, and again, this is part of that, so hopefully it wasn't too long-winded, but again, this is the first time we're going to see the bit shift operator, and we're going to see it a lot going forward. So I just want to explain what it does and why we use it. This is the alternative to using the multiplication sign and the division sign, and generally this is more efficient. The problem is that you can't use it for every number. You can only use it for powers of 2, so keep that in mind. It's not a silver bullet for every situation. Here we poll the inputs, and again, that can come back to here to where poll input is. I have it uncommented. And all this does is, again, we're not returning anything. We're not giving it anything of an argument in here. All we're doing is recording the keys pressed and keys held in a global variable. And again, we're using Devkit SMS to determine that. Here, it hands back a number that represent which keys are being pressed by bit, and we record that here. And then this one is for keys that are being held down, so we record that here as well. And then part of my randomization is that for the random number generator is that it's also based on user input. Typically when it comes to random numbers and computers, they're technically not random. So the idea behind this is that there is one random element that's going to be part of this game, and it is the player. The player is the random element. So whatever, at any point in time in the game, whatever keys are being held, what buttons are being held, whatever it is, it will be recorded here from our global loop. As you can see, it's the first thing at the top because we don't need to wait for VBlank for that. And we're going to record whatever's being held, if there's anything being held, and then we're going to times it. As you can see, we do the bit shift operator to the left. We're going to times it in this scenario with 3. If we go back to our chart back here, 3 equals 8. So this is the third bit, and this is the maximum value the third bit can have. So it's going to be 8. We're going to times it by 8 here by putting 3. I know that's a little confusing because it's not we're not putting 8 in there, but this is by bit. This is a bit shift operator, so we're going by bit, and the third bit, the maximum value can be 8. So that's what we're timesing or multiplying it by, because we're pointing to the left now. That means multiplication. So we're going to take whatever the keys held here, and I know this is a short or something of that nature, and we're going to times it, it's most likely going to overflow the random number generator, because remember that only can go up to 255, and if we go over that number, it's going to overflow, and that's what this basically does. It's going to take whatever keys are being held, and it's going to times it by 8 to add a little more depth to it, and then it's going to change our random number based off of that up here. So the original Miss Pac-Man, I should say, because Pac-Man didn't do this, but Miss Pac-Man, as it was a mod of Pac-Man, and what they did in the Miss Pac-Man for random number generation is that there's a register within the Z80 that is like sort of, I forget what it represents. It represents, I think, a number of either the number of lines of code that were executed, or maybe functions being executed, whatever it is. But the register is called the R register, and the R register was being used for the random number generation for Miss Pac-Man in certain scenarios that they go over in the dossier. Well, not the dossier, because that's just Pac-Man, but later on with the randomization, like we discussed, where Blinky and Pinky can randomly go to different corners of the maze or the stage. That random number generation was primarily done through the R register, and I don't want to go too in depth what registers are and what they mean to the Z80 and that sort of thing, but just as some context and background, we're not doing the same thing the original game did. That's more of what this is more modified. So there was two different ways that they did the random number generation between Pac-Man and Miss Pac-Man, but with the Miss Pac-Man one, with their programmers, they decided to take the pseudo-random number from the R register and then apply that as the random number. These next two functions is get row and get row offset. This is just because the vertical scroll, it kind of resets itself. So there's 28 total, and we'll look at this as when we go down the road, and we look. I'll show you within Emulicious some of the things there. We're gonna take a good look at what code is, what it looks like when it's being executed, and also how things look like when we scroll either vertically or horizontally. And typically we have 28 rows total within the mode 4 that the VDP uses by default for the Sega Master System mode. So it has 28 rows, and then once the scroll reaches that 28th row, it will reset back to 0. So we could do things using modulo, but since I don't even have 2 screens worth of vertical space to scroll, I'm just going to use a simpler method here where I'm just checking, okay, is the row that I'm being handed as the argument here, is it greater than or equal to 28? If it is, then I'm going to subtract it by 28. So that kind of represents it resetting back to 0 and vice versa. So like if it's less than that, then it just bring back the row. So here it's just a ternary conditional here. So what it means is here, instead of writing it this way with an if, and then we would have like an else, and then whatever else would be there. Instead of writing it that way, we can write it in a shorthand fashion. So here, all we're saying is, okay, the row that was given as a parameter or argument, is it greater than or equal to 28? And we have a question mark because we're asking a question there. This is part of that. So we're checking if it's this conditional. If it's true, which is our first result, so if it's true, then this is what we do. If it's false, and you can see it's separated by this colon here, if it's false, then we're just going to hand it the row that we were given. So that's what this statement says. It's in one line. I could write the same exact thing longer. So if I wanted to write the same thing here, I would put if, and then I would put in rows greater than or equal to 28, and then put this in here, and then I would give back that row of return row, and then minus 28, and then semicolon. You always have to have the semicolon at the end, and then else, and then we return row. And as you can see, that's a bit more syntax. This syntax is exactly the same as this syntax. This is just a quote-unquote shorthand way to write it. And while I say that, be careful, because sometimes SDCC, when it translates this shorthand way of writing your if-else statement, sometimes it does some wacky tobacky stuff where it might bloat up. Like one instance I had, I was using it, I forget what game it was, but it was very similar to this, very simple. And when I went to compile, I noticed that roughly 900 bytes went missing for a small change like that. And I was like, why did it use so much of my code space for this? And at first I didn't really think it was this shorthand return area approach to the conditional, so I didn't really weed it out at first. But then, you know, by process of deduction, it can only be this line, so, or a line like this. So once I changed it to the longhand one, which I just showed you, it like it gave me back like pretty much all my bytes back, except for I think like 6 or something, which is what I would expect. And when I looked at the ASM, as I said in a previous tutorial, you can keep the ASM around, and sometimes it's a good idea to do so, because it will, in the ASM file or the assembly file that it creates after it compiles, after SDCC compiles, it will show you each function that you have created, and it will label it out nice for you. It will, then from there you can take a look at what it may be doing, and again, it's a good idea to have some background on what the Z80 is all about, what this registers and how it handles things, at least, so you can see it was just doing a whole bunch of register switching, a lot of it, I don't know why, and it made this mountain of assembly that to this day I don't understand how it, or why it did it. But then once I went and used the longer hand approach to the conditional, it fixed everything, and then the amount of logic that it had there for that and an assembly was what I would anticipate from my experience with it. So this is nice, it's to use, but be careful when you compile. If you see a drastic change in how many bytes you have left in your bank 0 or your bank 1, you might want to go back and, you know, this might be your issue. So I only had it happen to me really one time. From what I understand, you can mitigate it if you put parentheses around certain things. I think if you put these parentheses around it, it will help mitigate that, I think, a little bit more. I never used it, but that's what I've read, at least. So and I even think that might not even be 100% fail safe. So, but I do it here anyway. So, and if I look back to the assembly on this stuff, kind of double check to make sure that even though I don't know assembly inside and in and out, you can see when there's a lot of code that's being applied to a section. So that can be an indicator that you may need to maybe use the parenthesis approach, or just convert it to using a standard syntax for that. So again, it could be a gotcha there. So that's what we're doing with get row, and this get row offset sort of does the same thing, but it does it in a tile, not a byte address format for when we go to use one of the functions that that SMS Devkit supplies us. So it's the same thing, but this is based on tile. This is based on actual bytes. So we'll see that later. Okay, and this is get tile ID. So all this does is we feed it at the index. So that index is what we have here. So we show tile and the tile index. So we give it an index, and then all it tells us is what the tile ID that's underneath it without the other bits in it. So we'll only take the tile ID number itself. It won't take the other flags that are associated with it, like the horizontal, the vertical, the priority that we showed, the type, all that, or the 3 bits that aren't being used, that sort of thing, or the palette. So it won't take any of that. It'll just take the raw 9 bits that can go up to a maximum of from 0 to 511 or 512 values altogether. So I would say if we fed it 847 as the index, it will spit back 258 because that's a pellet there. It'll spit back that ID, and we use this, as you can guess, as the player is going around the map, and it goes into a new tile. It goes from its current tile into a new tile based on its position. It's going to check that tile that it's sitting on for a pellet. So we'll hand it an index depending on what the current player is. So if it's player 1, we're going to get it from our player 1 map, as we showed over here in globals, that player 1 map. So its current map that it's going through, sort of the stage that it's going through. It's going to point into that tile data, or the tile set data, or tile map data, I should say. It's going to go and look at that one square, that one tile all the way here, based on, again, the index. So it's going to go to the 847th tile within the data, and then it's going to pull back that value. So the value that's in there is a short that is representing our tile ID, our other flags that we have there, the horizontal and vertical flip, so those 2 bytes, like we discussed way back when Maxim was talking about this, those 2 bytes, that value will lie in that data. So we can point to that one single tile there, and then we're going to ask, okay, what's the tile ID? Normally it would give us 2 bytes, but we're only interested in, and it still will only give us 2, it will still give us 2 bytes because it's short that's returning. But what we're going to do is going to mask off, and that's what this syntax here does. It's going to mask off everything that we don't need. We just need the 9 bits. So remember, when we look at the power of 2, remember how 9 equals a value of the maximum value of 512, 0 to 511. So we're just interested in those 9 bits. Again, going back to maximum, those 9 bits that we need from 0 to 8 here, that tile number. So 9 bits, because 0 to 8 is 9 values. We're only interested in that. We're not interested in anything else. So that's what we're doing here with this call, is we're masking off only the tile ID. We don't care about any other stuff. We just want the tile ID. And what we're going to do is, if it's a certain tile ID, then we're going to condition on it. So if it's a pellet, we're going to then clear out that tile to an empty tile because we just consumed it, or the player consumed it. And then we're going to increase the player's score because they ate the pellets, 10 points. They get 10 points, and we're going to update things. And then we're also going to make it that we have a flag that since we ate a pellet, then we're not actually going to move this frame. So there's a bunch of things that can happen here. And another example would be to say that, all right, the index we might give it is, we're checking for walls or solids. So here we're maybe checking something that's a solid, and say the player is going along and it reaches to this tile and they still want to go to the left. Well, this tile here, if we go to IDs, shouldn't let them because it's at 350. And you recall we have define a constant that says anything that's greater than 340 is a solid. So when it gets this tile ID, it says it's 350. We know it's greater than 340. This is a tile that the player cannot move into, or a ghost, or whatever. So again, that's what we'll use, is get map tile ID. It's actually a very important function, and it will be used constantly throughout the game. So once it figures out that tile ID is going to return it as a unsigned short, and then we can use that for further conditioning and logic within the game. So now we got a value. Here, we're actually going to take a value, and we're going to set that within the... We're going to first set it within the whatever the current player is, whatever that P1 map or P2 map, and we're going to set that value based on where the entity is. So let's say, and again we'll use the player or Miss Pac-Man thing again. So when the player runs over a tile and we check what that tile is, if it's a pellet, now we have to go back and change it from a pellet tile to an empty one, and the empty one would be a value, in our case should be 256. So if you take a look at it, 256 is our empty tile. So now we're going to send it to that. We do actually have a define for that. So under tiles, we have one that's empty. Here we have is 256. For the ones that are solid that we need to check, it's over 340. So that's where we set that. So we would probably just give it this constant. So we would set wherever that value is. So here, and then we're going, this index is the actual player, or whatever the entity is. So if the entity in this scenario would be the player, and we would go to their property, the entity tile. This means the current tile that they're on. We're gonna give it the index to player 1. So here we're only interested in player 1's current tile that it's on, and then that's what we're gonna use for index within our player 1 map. So we're gonna use the player's current tile. We're gonna use that our index in the player 1 map. And then wherever that player is on top of, we're going to give it the value that we're sending in here. In this scenario, we are giving it the empty tile value, so 256. So now that we set that in the map, that's all cool and everything. But we also have to update the visual representation on screen. So on VRAM, we need to also update that. And we're going to check if the entity is visible within the map. And why do we do that? Because player 2 might be off the map, and if we update the screen, and this is a bug that I discovered later, if player 2 is eating pellets off the screen at the bottom of the screen, it will actually affect the map in an adverse way. So we only care to change the map if the player is in view. So again, so we're going to check if it's if the player's in view. And then if it is, then we're going to start changing the map tile that we have. We did it here in the player 1's array, but now we're going to do it on screen. And again, why if it's in team play, why would you need here? Is because in team play it is in one player mode. So that's why we would check it here in view, no matter who it was. So if the index is a current player is index player 1, that's how it is in team mode, because they're in team mode. Player 1 and 2 are sharing the player 1's index on the gameplay. So if the current player is player 1 here, that's true in team mode, and it's also true in single player mode. The only time it's not true is when in 2-player mode, where they're alternating. So the map does change there. But when we're in team play mode, where it's the current player will always be this, and that's why we're making this check with it being in 1-player mode. So some background there. Sorry about that. So we're going to check the entity's visibility. So that could be player 1 or 2 in team mode, or it could just be player 1. We're going to see if they're in view. If they're in view, then we will allow them to make changes graphically on the screen, and that's where this happens. So this happens in memory, so we remember it, and this one actually happens on the current screen and VRAM as long as they're in view to do so. And we're going to use this call here, load tile map area at address. Why do I use it? There's two different, there's more than that. There's multiple ways you can update the tile map on the VRAM through the VDP that Devkit SMS allows. The reason why I picked this one is because the other methods, they want a column and they want a row that they're going to change. But I keep the information, the index, and the tile is actually a short. So it's just a one single numeric value. It's not an X and Y or a column or row. So that's why I use this. So I would feed it the current tile ID. So tile ID, there's a lot of complexity here too. So the tile, any tile ID is a short, but in the data, since it's a short, there's a multiplication here of 2 to add up correctly on the data, and then it's tile map 0. So we're adding where the tile map data starts, and then we're going to add our tile ID to that, or our tile ID where we're at, and then we're going to do that get row offset here to if it would happen to roll over in the vertical scrolling. Again, we're going to then use our actual pixel value, and we're going to divide that by 8 because 3 equals 8. Oh my god, this is getting more complicated the more I talk about it. And then this whole math here will give us the destination and our VRAM addressing. So that's what this whole calculation is, to get the point in the map. That's our destination. Then we're going to feed it the value that we want, or what that source is, so our source value. Since we already changed the value here, we're just going to use the same thing for this. So we're going to, this ampersand in here is saying we're pointing into this map data, we're pointing to it in address wise. So we can then pull the value that currently just got changed, because here P1 map, this is where our player is, and then this was the value that was changed, so it should be the same thing here. So as you can see, we use that value that we just set, and that's the value we're going to use in this argument for this. So that's our value. So destination, our source value, the width and the height. So this thing can do more than one tile at a time, but we're only interested in changing one tile here. So the width is one. It's not the width of a tile in pixels, it's the width of a tile as a tile. So like a column or a row, it's an actual tile. It's not, where is it? Actually, I don't remember. Unsigned car, it may or may not be. It doesn't matter. We're going to give it 1 for the width, and we're going to give it 1 for the height, because we're only changing one tile. So that's what this does. This whole long-winded thing. And the only way you could do it another way. They have a low tile map address area added. You don't have to use this. They have another one that has a low tile map area, and we can see that. And then there's another probably speedier way where we can use unsafe methods, like we kind of discussed towards the. I think it was up towards the top, where we can use an unsafe fast call to just write 2 bytes there, but that I don't believe we have anything for that yet, or maybe there is and I just don't remember what it is. But Devkit SMS has a lot of options, so that's what we're using here. Like I said, we'll go over the other variants of this as we go along that are safe, and the other unsafe calls that we can make. Generally, unsafe calls are way faster than using the safe calls, and the reason why we use the safe calls, because we might need to use that call during active display, which I'll go into later, versus when we're in VBlank or when the screen is turned off. Let's see. don't have too much more to go. So here is a very important function, update row. So what does this do? So when we hardware scroll a tile map, it doesn't just automatically update for us. We have to actually update the row either before or after where the direction that we're going to scroll. So let's see how I can put this. So let's go to the area. So this is our visible screen, as we've gone over a bunch of times, where the amount of columns is 32 or 256 pixels in width, or 32 columns in width, or we can go 24 rows or 192 pixels. This is what our screen, our viewport is. And as it scrolls down, it isn't just going to automatically update things for us. That's just not how it works. So when we start scrolling down, we need to draw ahead of where the scrolling happens. So if, let's say, this is the view we have, and the player starts scrolling down. As it scrolls down, it needs to fill the row just before the viewport as it's going down. So it'll fill here, and as it keeps going down, then it'll fill again here, depending on where it's at. And then it'll just keep one row ahead of what the player is going to see. So we need to update that, and it can only update till it gets to the bottom here, as we discussed before, is 96 pixels. So when it goes down here, then it starts, if the player goes up, then it has to update the row that's up top of this viewport, and then as it's going up, it's got to keep updating the row just before you get to it. That's how we update the graphics during a scroll. So it doesn't just happen automatically. You have to have some sort of code in place to do that. And this is what this is. So what it takes for an argument is the direction that the scrolling is going to happen. Then the amount of scrolling that can happen is variable. So in Pac-Man, Miss Pac-Man has a bunch of things when it comes to speed. Depending on the stage that she's on, it has certain speeds. So she gets faster in certain stages, and as you progressively go along playing the game. And then also there's the speed boost or the pack boost, which is about equivalently the double the speed. So I want to make sure that the viewport stays, or the scrolling stays with the player. So if the player is going double the speed, we're going to add that in here. If it's not, then we're going to add our base speed here, whatever I mean by pixel here, so it can scroll smoothly with the player. So that's the idea of that. So there's only two things really here. It's either you're going up or you're going down. There's no left or right, because again, we're only vertically scrolling only. So we're going to check if the direction is down, so we're going to scroll down. Here, this is our failsafe to make sure that we don't go beyond that 96 that I was talking about. So it's going to take, this is our actual global variable that's going to hold where we are currently in the scroll. Again, like I said in the previous tutorial, it starts at 0, and then as you scroll down, it increases. As you scroll up, it decreases. So the minimum value can only be 0, and the maximum value can only be 96. So that's what we're checking here. We're going to see if we add this amount, whatever it may be, is it going to be greater than or equal to our maximum value here. So we're going to check the threshold here. And if it will be, then we're just going to hard code it to 96 for our scroll. And then the scroller is going to be none at that point, because there's no scrolling to be done. As I said in one of our previous videos for the global variables, that the scroller is the index that's causing the scrolling. So it could be player 1, or it could be auto scrolling, or in the future it could be player 2 that also does the scrolling. Right now that's not implemented, but in the future it could. So then we're going to take whatever that scroll Y amount, that universal amount that offsets every entity as we're scrolling. We're going to zero that out, and then we're going to set through Devkit SMS, we're going to set the hardware scrolling based on whatever our scroll value is at that point. So we're going to set it there, and then that will update the screen. That's only if we meet the threshold. So essentially hard code everything at that point. If you're too far, or you're trying to go further than the scroll allows. Else, we're just going to do the scroll update. So we're going to increment the scroll Y, our current scroll Y, where we are, the 0 to 96, whatever it is. We're going to add the amount that we want to add. So here it might be 2, it might be 1, whatever it may be, whatever the speed is for the player or whoever is calling, or what entity is calling this, whatever the amount that they want to apply, it will be applied to the scroll Y here, or vertical scroll Y. And this is just saying, just add the amount here. I mean, you can also do where you could say scroll Y and then that, and then you would add the amount, and then that would be the same syntax wise, but we're going to use the sort of the shorthand here. So just throwing it out there. So then we're going to increase the amount to the scroll Y. Then that scroll Y amount, that offset that gets applied to all the entities while we're scrolling, that will be, since we're going down, we need to everything else to go up by the offset. So we're going to give it a negative number. And as you see that we made that just a regular car or signed car, so it can be a negative number. And typically it will just be -2, or it'll be a -1, or it'll be whatever it's calling here. Typically though, it's like 2 or 1, but it might be more than that, so you don't know. So this will be applied to the entities that get called. Their logic gets called later, and then they'll offset the sprite based off of this value. And then we actually use Devkit SMS to do the actual hardware scrolling, and we're going to scroll it by that value that we just incremented. And then here is where we need to go into our tile map and get the row within their memory map. So here we have play P1 map as we showed it back in globals. Here's the one for P2 map. And what we're going to do is, again, we're going to use ampersand. So we're going to point to this data address, and then we're going to get the value of the current row that we need to update. So how would we figure that out? So what we would take is whatever our scroll Y is, and then we're going to add 200 to that. So why do we do that? Because this is 192 here. Adding another tile worth, or a row's worth, is, as you recall, the tile is 8 by 8 pixels. So we're going to add 8 so that we can render just below what we're scrolling to keep ahead of it. So that's what we're doing here. We're going to add 200 to whatever our scroll is. If you recall, our scroll is actually based at, here's our origin of the scroll. So as we go down, this is 0 here. As it goes down, it can only go to 96 and then go back up. So our origin's here. So it's whatever the total amount of our viewport is, which is 192, and then we add 8. So that's where 200 comes from. So now we know what row to go at when it comes to our pixel value, because remember this by pixels. Now we want to figure out the row, because all those 192 we got to divide by an actual tile amount, which is 8. So here again, like we talked about earlier, if we're shifting to the right, we are dividing, and 3 is the bit that we're going to shift by. So when we go back to Wikipedia, we can look at 3. That's 8. So we're saying divide by 8. So whatever our row here is, that we're going to divide by 8, and that's going to give us our row count, where to draw our next row. Then we're going to check the current player, if it's player 1 or if it's in T mode, because they use the same player 1 map in T mode. We're going to then use this call here, and this is a very important call. This is the unsafe version of copying bytes to the VDP and to VRAM. And I use this, and again, I only will use this when the V blank just hit. So I'll call this is one of the functions here, the update row, that I will call immediately after the V blank, so I can get the most out of the performance of the unsafe version of it. Like again, there's this writes to the VDP the fastest without messing it up. Apparently you can write data to the VDP too fast, and then I don't know the inner workings of that, but that's what I've read. You can actually write to the VDP too fast, or through the port, and I guess the data doesn't always get there. It gets corrupted. I don't know. I just know that there's a timing thing here, and Devkit SMS shields us from that sort of logic. The developer who made it knows the ins and outs of how that works, so that's why is also a benefit to using this library. So we're going to make an unsafe call. So our fastest call that we can possibly make to write, we're going to write 64 bytes to the VDP. Why 64 bytes? It's only 32 tiles Xfixium. Why are we writing 64? Because you have to remember those tiles are 2 bytes a pop. So that's why we're writing 64. So even though we have 32 columns here that we have to write one row for, so again, columns go horizontally, rows go vertically. So even though we got to write one row with 32 columns, each one of these tiles is, again, 2 bytes of pop. So that's what we're going to do. We're going to write 64 bytes. We're going to start at that address that we were talking about before, where it starts our tile map data. Then we're going to get our row. Here we're going to do it in a way that is per tile, because if you remember, our row is already divided by 8. So this is, now we're going by tiles at this point. And then we're going to take that, whoever that current row is, we're going to then times it by, I think that's 64. I may be wrong, but I'm drawing a blank here. Yeah, 64. So now we're going to times that by 64 to get our destination in memory and VRAM. So that's how we're going to calculate our destination. And then we're going to feed it the data that we're looking for, or we're going to feed it the starting point of that data. So it will take 64 bytes no matter what. So we don't have to define a size, because here it's specifically looking for 64 bytes. We don't define how many bytes, because obviously 64 is what it's going to take. So all you need to do is point into the P1 map where that data starts, and then this will copy it from the data here. So this is our destination, which will be our tile map data, and then this will be where the data actually is. So it'll be a P1 map, and we're going to go by row, and then we're going to times that by 32. Bit 5 is 32 max. And why do we do it that way? Is because even though we need this is done in bytes, this is actually unsigned shorts, so we don't need to go by 64. We instead go by 32 at that point, because the P1 map is full of shorts. It's not, if it was full of bytes, it would be double this number, and then we'd have to use 6 as our bit. But here, since it's kept as unsigned shorts, that's what we're going to use here. So we're just going to times it by 32. Again, shifting to the left is timesing or multiplying. So, and then 5, if we look at our bittiness, it will be 32. So 5 will equal our 32. So we're just essentially saying, all right, take our whatever current row is that we're at, and then we're going to times it by 32, and that's how we're going to get where we need to be in the map. I don't think I really need this, but I put it in here anyway. So this does the same exact thing that this does, but instead of calling an unsafe call, we're now just calling the normal version of it, which is SMS load tile map area. So here it just would load up a tile map area by tile. So again, it would get the row, and then 0 is the X. So if you look at the parameters as X, Y, this is actually the current column you want to write to. It's not an actual pixel X. And then this would be the row that you want to write a tile or series of tiles. So what this does is you can set how many tiles it can write to the VDP. Here I'm going to start at 0, because when we look at here, 0 is where the X position is going to be here. So when I roll over here, as you can see down here, X tile position is 0. So it's always going to be 0, because then we're always going to write an entire row's worth of information. So we're going to start here. The only thing that's going to change is what row that we're currently drawing on. So that's why we get the row here, and then we're going to get we're going to use the same logic we used before to get the beginning of where our data starts by using this ampersand. We're saying, okay, this is where our data starts, and then here we can actually specify how many bytes we want to actually write to the VDP, and we go by the size of the width of the area you want to draw, which again is tile based. So 32 tiles we want to have, or 32 columns worth of tiles, and then we only want to write one row, so that's why we have 32 by 1. It's more readable than this, the unsafe version, but it essentially does the same thing. But the reason why we do it here is whether we are in VBlank or not, when we write this data to the VDP, it won't corrupt the screen. It will be done in a safe manner. It will be slower if it's done during well, I don't know. It might even be slow when on VBlank too. So it will just be a slower method versus my God, Windows. It will just be a slower method when it goes to write this information. So that's the difference. But this will be safe. So if I would write this while we're in active screen, while it's the actual display, active display, would corrupt things. This would not. And the only reason why I put this here is situations where I'm scrolling, but it's on the load method, or a method that's not where I'm actually running the game engine. So it doesn't need to be performant, but it does need to be safe. So that's why I have the same thing. And really, I could probably get around this if I would just wait for VBlank again before I call this method, but I like to be more safe than sorry about that. So again, the only difference between this is that this is a safe method in active display, and this is where we're going to get our most blazing fast results, and that's right after the VBlank. All right, and then the last things for the common, it just has to do with that act clacker that we talked about in the global variables. This is where we just need to draw a sprite, so we'll get into that later. I don't want to go over Metasprites at this point in the series, but we're getting to it soon, and I'll describe what Metasprites are and how there's various ways that we can do it with Devkit SMS, but it has a dedicated function for Metasprites, and I sprinkle that everywhere I can get. Generally, I think, based off of some of the things that I've read, that this is pretty much the fastest way to get a sprite out there. So I generally use it wherever I can at this point. And we'll go over that and what the differences are, because there are a bunch of different functions that Devkit SMS allows for you to draw your sprites. You don't have to do it with a Metasprite. It might make more sense to piecemeal your sprites instead of creating these compound sprites that you can define. So update act number. So all it does is we're given it a X and Y position. This is pixels positions because we're dealing with sprites. And then what we're going to do is we're going to create a small definition for a Metasprite. So this Metasprite end is a constant that Devkit SMS provides for us. So the format is that we typically have for a sprite is that it has an X position by pixel, not by column or row or tile, and as a Y position that is by pixel. So here we're saying we're drawing the pixel definition is that the offset for it is starts at 0, its origin's at 0 for the X or horizontal position, and its origin for the Y position is at 0. And then this is the tile that we're going to use to represent the sprite. So it's graphic. So we're going to say 164. And we'll get more into that as we go into the cutscenes, because 164 is where I will put the current number for the act. That's the tile number I'll always put it into. That's why it's always static here. And then at the end, because you can define way more than just this as one, because remember sprites are these 8x8 pixel blocks, so we can define more than just one here. So we're just defining one block, or if it's in tall mode, we're just defining one 8x16 or two of the tiles. when we're in tall mode. But so we can define a lot more to it. You can put those together to create more complex things, and I guess I could show something like that. So let's kind of give you a better idea, and we'll go more into this. I'm just let's look at TMNT. I want to say this is the latest and greatest. We'll see. So Metasprites, and we'll keep it down in size. So we'll see how complex some of this stuff can get. So we have Leo. Let's do a cool one. Yeah, here we go. So for Leo, like I said, we have two modes. We have either normal or tall mode. Here we're using tall because we're trying to get, since there's a limitation to how many sprites we can draw on the screen and how many sprites we can put in a horizontal line, we need to be as optimized for the game as possible. So it might make sense that we want to only have it into the original sprite mode where it's only 8x8 pixel tiles, and then it might make more sense to have it in tall mode where it's 8x16 tile sprites. And so here I show what Leo looks like and his one attack, the attack where you press both buttons at the same time. And this is how I would get it to offset, and I could show you how these sprites, when they're put together, they create a whole graphic. So that's what I'm trying to convey here. So the origin, again, as I talked before, is our origin starts at 0, 0. That's where this offset plays into. So this number that we're talking about, that's what that origin or the offset would be. And then here, as we go through each one, we can see where we have the sprite located. All these tiny sprites, they create the entire image, as you can see. And here you have the sword here and whatnot, and this actually goes into the negatives. You can see our vertical value is a -8, so the offset would be placed a little higher than our origin. Our origin here is 0, 0, so it would be placed a little higher. And we can, within SMS Tile Studio, we can play around with those values. You can move them up and left and whatever. We can move them around if we wanted to, or we can move the entirety of the sprite here, and we can move it around if we want to, or we can just move one piece around, or however way I needed to get it done. This is how I got it done. So we have that for our first frame, and then the second frame we can see what all those values would be selected and how they look like. And sometimes you got to get a little crafty, and TMNT is one of those games. It's very demanding. The amount of sprites on screen will almost certainly always be close to the maximum amount that we can use. So you have to be a bit efficient with it. The maximum amount of sprites that any one of the entities can use for the turtles is a maximum of 10. So they can use 10 sprites total, which is pretty big. It's pretty chunky for the Master System. And then I think for the foot, it might be like 8 or something. 8 or 10. Maybe it is 10 for them. I don't remember. So then, this would be, you can see how it offsets just a little bit, because the way that we want the graphics to fit in, we need to be as optimized as possible. So it shows that frame, and then we go to the next one, and it shows that this is more in line with the grid aspect of it, but we might even be able to get rid of one of the sprites here. But so then that's what it shows there. And another good, I think, one way to look is also how the flipping was done. So if you take all these, here it's 5 sprites total. If we would do this by a normal grid situation, it would actually take 6. But as you can see, the head is just offset just a bit from the rest of the graphic, so it only uses 5 here instead of 6. It's a cost savings because, again, we try to limit how many sprites in a row or in a scan line, because remember, we have that limitation of 8 before we start flickering things around. So we want to try and avoid as much of that flicker as possible by providing the least amount of graph or sprites on the screen at one point or at one time. So we try to be optimized about it. So that's pretty much how it works. But yeah, so these are some of the animations and stuff. So kind of felt like that was helpful in some way, hopefully. So, all right, and that's what we have for TMNT and sprites, and we'll go more into it as we start creating them for the game. So that's what we do. So we're, for each one of these update our acts, so there's 3 acts, but there might be more. We might have a 4th act if we want to end the game. I know that's what they did in the original version of Miss Pac-Man. So we might want to do that later, but right now all we have is the arcade classics original 3 cutscenes. So that's what we're going to use this for, to show the number on the clacker, because the reason why we do it is that the number actually doesn't fit in a tile very well. So we do it in a sprite instead of the tiles that we defined when we looked at the title, as you remember. When we looked at that clacker, it doesn't fit in the tiles here. If we would try to put a 1 or a 2 in here, it would create way too many additional tiles that I'm not comfortable with. So that's why we're going to use a sprite instead, since we already have those numeric graphics already, and we can just load them into VRAM whenever we like. So then we have the update clacker, which is just updating animation. Here the X and Y is actually tile positions, I believe. Yes, because we're using, again, that same safe call that we did before, where we're going to update the graphics are on screen with the animation. So if the clacker frame is at 0, it will create the first animation, which is the one where it's wide open, and then it'll also write the bottom portion of the clacker to the screen, and then it's going to increment the frame of that clacker by 1. And then here we do have another switch case statement where whatever this is, when we increment it by 1, that's the animation we're going to use to show. So as you can see, it's only the top portions of it. So whatever that frame of animation is, it'll update the screen accordingly. So we'll give it the idea that we're updating or using animation. So, it would use the closing, and then it goes back up to the top, and then once it reaches a certain frame amount on the calling code, it will stop, and it will run the rest of the game state through incrementing the substate. So we'll see more of that as we get along. I believe that is everything for this. Hopefully it all made sense. I know it was a lot of information, so I don't blame you if it was very confusing. I hope it made some sort of sense, and as we go along, I feel like it will make more sense as we delve into the player stuff and the other entities like the ghosts and whatnot. But thank you for watching, and I hope you got something out of this, and I'll see you on the next one.